Okay. .9 is representations of functions as power series. Let's try to write better. Presentations of functions as power series. Okay, from the geometric series, remember those guys? Okay, we can derive 1 plus x squared plus x cubed plus ... plus x to the n plus forever. Okay. This is the summation of n equals 0 to infinity of x to the nth. Okay, and this guy here, it converges if if the absolute value of x is less than 1, it converges. So this series here, this infinite series, okay, I can write as a sum. So this is the summation as n equals 0 to infinity. And this, of x to the nth. And this becomes 1 over x, 1 minus x. Okay, as long as x, the absolute value of x is less than 1. Okay, remember that because this is a geometric series and the common ratio is x, then we can say this thing converges and has a sum, okay, of 1 over 1 minus x, whose, where where x is the common ratio. As long as the absolute value of x is less than 1. Okay, so we can say that this function, this f of x equal 1 minus x, okay, is equal to 1 plus x squared plus x cubed plus x to the nth, okay, plus ... goes on forever, okay, which is equal to the sum of n equals 0 to infinity of x to the n. That's a function of x. We can represent that as a power series for small x. Okay, absolute value of x has to be, basically x has to be a fraction. That's less than 1. Okay, fraction or decimal that's less than 1. Okay, positive or negative. Okay. So this guy is the series representation for the function 1 over 1 minus x. Okay, that's the series 1 plus x squared plus x cubed all the way to x to the n. Okay. Let's use this idea to express the function 1 over 1 plus x squared as a power series. Okay. Well, I can think of this 1 over 1 plus x squared and put it in terms of what we have above here, I would go 1 over 1 minus negative x squared. Okay, and so let's go term by term. What is this going to look like? It's going to look like 1 plus, instead of plugging in x, I'm going to plug in negative x squared plus negative x squared squared plus negative x squared cubed plus dot 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 negative x squared to the nth, and it goes on like so. And so what happens is we get an alternating series, and it goes by even powers. This is minus x to the 6th plus, you could have an x to the 8th there, minus dot dot dot. Okay, and this becomes a minus 1. I'm going to break this up. Minus 1 to the nth times x to the 2nth power, because power to a power, you just multiply, plus dot dot dot. Okay, and so we could actually rewrite that in summation notation. Okay, as n equals 0 to infinity of negative 1 to the nth power, it alternates, and it's just x to the 2n power. Okay, and so that was equal to 1 over 1 plus x squared, as that written as a series, okay, in an infinite series. This whole, that's what this whole chapter is on, is infinite series. Okay, differentiation and integration of power series. So we can integrate and differentiate to get various other functions, and put those functions in terms of a power series. Okay, write them as in terms of a power series. So theorem. Okay, if the power series summation Cn, which is some constant, okay, x minus a to the nth power, okay, so each term will have a different constant, okay, has radius of convergence r greater than 0, so some positive r, then the function f defined by f of x is equal to c naught times x to the 0, which is just 1, plus c1 x to the first, or x minus a to the first, which is just x minus a, plus c2 times x minus a squared, plus c3 times x minus a cubed, plus dot dot dot, okay, equal to the summation of Cn x minus a to the nth power is n equals 0 to infinity. Okay, if this function, this power series, okay, is differentiable, and therefore continuous, on an interval I should say on the interval. Okay, this is centered at A, so it's going to be A minus R to A plus R. A is the center, and R is the radius of convergence. Mm. Then we can simply differentiate term by term. Okay, and so f prime of x is going to be equal to c1, okay, plus 2c2 x minus a plus 3c3 x minus a squared plus dot dot dot, okay, which is equal to summation as n equals 0 to infinity of n, okay. So I have 1, 2, 3, n, okay. And we can start at 0 because we would just get 0. Okay, Cn x minus a to the n minus 1 power. Okay, so all I did was bring the n down and put it in front, and then subtracted the power by 1, which is just the power rule. Okay, and I do that for every single term. Okay, 2. If I want to integrate term by term, then instead of subtracting the power by 1, I would add the power by 1 and then divide by the power. Okay. Okay, so this is equal to c, and c is just a constant of my constant of integration. Okay, it's a constant term. Okay, plus c naught x minus a plus c1 over 2 times x minus a squared plus c2 over 3 times x minus a cubed plus dot dot dot, okay, equals summation. Actually, I need to put my constant c there first. C plus the summation of c to the n over n plus 1 times x minus a to the n plus 1. Okay, and this is n equals 0 to infinity. Okay, so basically this is just saying in kind of a long way is we can differentiate term by term and we can integrate term by term. Okay, if we want to get the integral or the derivative of, okay, a function, a power series, a function that's represented by a power series. Okay, let's use this idea to get this guy here. Okay, express, okay, 1 over 1 minus x squared as a power series. Okay. Okay, and I'm going to use the fact that, okay, what I have here is the derivative of 1 over 1 minus x. Okay, is that true? If I take the derivative of that guy, okay, do I get this guy? Let's verify that. 1 minus x squared. Okay, is the derivative of 1 over 1 minus x, which is the power series that we've been working with. Okay, and so let's write this a little bit differently. Let's go d dx of 1 minus x to the negative first power. Okay, now let's do the chain rule on this. This is going to be negative, bring the negative 1 down, and I get 1 minus x to the negative 2 power times the derivative of 1, which is 0, minus x. Derivative of negative x is negative 1. So I get the negative 1s to cancel, and I get 1 minus x to the negative 2 power, which is 1 minus x squared. So it does check. Okay, so if we take our original power series, 1 plus x squared plus x cubed plus dot, 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 okay, plus x to the nth, okay, that's equal to n equals 0 to infinity of x to the nth, okay, because the constants here are just 1, okay, and we take the derivative of that, okay, we differentiate term by term, then d dx of 1 over 1 minus x, okay, this is equal to 1 over 1 minus x squared that we just showed that from above, okay, so from above. Okay, but we're just going to take the derivative of each term here. This is 0. This is 1 plus 2x plus 3x squared plus 4x cubed plus dot, dot, dot. Okay, and then the nth term is just going to be x to the n. Okay, x to the, or it's n, x to the n minus 1. Okay. Plus, I'm going to do one more term. I'm going to look at not only the x to the n term, but I'm going to look at the x to the n plus 1 term. And there's a reason for that, because we eliminated a term here. Okay, and so if we want to start at 0, I'm not going to want to get 0. Okay, I'm going to want to start with 1. Okay, and so this would be n plus 1 times x to the n. Okay, plus dot, 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 okay. Okay, I mean, we could start with 0 if we really wanted to, but we could back this out by one term. Okay, and we could say that, although, again, here's the idea, is that this 1 here, that 1 is really x to the 0, right? Okay, and this guy, yeah. And so this is really 1x to the 0 power. Okay, and then so what would this guy have to be? This would be, I guess this would be 0 x to the negative first power, which is kind of interesting. Okay, so that's really 0 over x, which is just 0. And so you could start either place, but it just makes it a little bit cleaner if at 0, at my beginning n equals 0, I start with the 1, which tells me that this is going to be n plus 1 x to the nth. So it's a little nicer to just start with 1 x to the 0, which is just 1, and then go to 2x to the first, and then 3x to the second, and then 4x. I like the n plus 1 because it just tells me that my index for my constants here is 1 more than my power. It's always 1 more than my power. And so I like the n plus 1, you know. You could do it, again, you could do it with the n and the n minus 1. That's fine. Either way, it's just my preference is to say, oh, I have the nth term, and then that's going to be n plus 1. Okay, so to me, it's a little bit cleaner. Okay, number 3. They find a power series for the natural log of 1 plus x and its radius of convergence. Okay. Okay, number okay, so the idea here, again, is that we can integrate this thing. If we take the integral of 1 over 1 plus x, right, then that's the natural log of 1 plus x. Okay. Okay, and so the natural log of 1 plus x is equal to the integral of 1 over 1 plus x. And what was 1 over 1 plus x? We did that and we didn't do that one. 1 over 1 plus x. Okay, this is going to be the integral of, okay, 1 over 1 minus negative x, which is going to be an alternating series. Okay, that's the integral of 1 plus negative x plus negative x squared plus negative x cubed plus negative x to the 4th plus dot dot dot. Okay. So this is the integral. I'll put a little dx there. The integral of 1 minus x plus x squared minus x cubed plus x to the 4th okay, minus, and then, you know, however many terms out you want to go. Okay. And this would go out to, let's go out to the nth term here. What would the nth term look like? It would be negative x to the nth, right? Okay. Yes, yes, like that. Okay, so now, okay, we want to integrate each of these terms is dx. This is dx. Okay, so let's see what happens. We get our constant. Let's put our constant there. Okay, plus. Okay, the integral of 1 is x. The integral of x is this negative 1/2 x squared. This is going to be plus 1/3 x cubed minus 1/4 x to the 4th plus 1/5 x to the 5th minus, and then this is going to go on forever. Okay, after we integrate. Okay, so let's look for a way to write this as a series. Okay, so C plus the summation. Okay, of what? Well, if we start with n equals 0, okay, we would have to do an alternating series of -1, but I want that to start off positive and then go negative. So that makes sense. If I have a 0 there, then I have -1/n. Okay, that makes sense. Okay, and then start with the x there. So x to the 0 power is 1. I don't want that. I want x to the n plus 1. Let's add 1 so that we get x to the first power. Okay, and then this is going to be all over n. Okay, but there's a problem. Okay, but n cannot equal 0. Okay, so we're going to change, and we're going to start, instead of letting n equal 0, we're going to start with n equal 1, because I can divide by 1, but I can't divide by 0. So if we let n equal 1, how would we create the same series but letting n start with 1? Well, I could easily just change where the -1 starts off. Okay, if I do -1 to the n plus 1, then that starts me off. I'm sorry, we want 1 here for n equals 1. We want that will start me off with at 2, which will still be positive. So if I take 1 here, and if I add 1, that'll give me that. And then if I subtract 1 from n plus 1 and just make it n, then that will give me my x. Okay, and then if I divide by 1 to give me my x, that's dividing by n. Does this still follow? Yes, this still works. Okay, and so that is the power series for the natural log of 1 plus x. Okay, it's some constant plus this. Now, that constant is problematic. What's the constant? Okay, well, we can actually solve that, solve for this constant. Let me show you how. If we back up to this line here, and we say that the constant plus x minus 1/2 x squared plus 1/3 x cubed plus 1/4 x to the fourth plus, whoops, it's a minus, sorry, plus 1/5 x to the fifth plus dot dot dot. Okay, notice that every single one of these terms, except for the constant, has an x value. And supposedly that's equal to natural log of 1 plus x, right? And so what is a convenient value to use here to solve for the constant? Well, if I let x equals 0, then thing goes to 0 that involves an x. So this is just going to become the natural log of 1 plus 0 is equal to c plus 0 minus 1/2 0 squared plus 1/3 0 cubed. And again, these all go to 0. So this whole thing gets wiped out. And I'm just left with the natural log of 1 is equal to c. Well, what is the natural log of 1? Yeah, 0, right? So we can actually solve for c and let c be, and find out what was the constant that had be, and it had to be 0. So we actually get this guy to go away. And so the natural log of 1 plus x is equal to the, that goes away too, equals, I'll just write it as the summation. Summation as n equals 1 to infinity of negative 1 to the n plus 1, x to the n all over n. And that's the power series for natural log of 1 plus x. Okay, now it also asks me, what is its radius of convergence? Okay, what is this thing's radius of convergence? Well, okay, we could use the ratio test here to find the radius of convergence. Would kind of be nice. So let's do that. Take the limit as n goes to infinity of the absolute value of an plus 1 over an. Okay, and so this is going to be negative 1 to the n plus 1 plus 1. Okay, or n plus 2. X to the n plus 1 all over n plus 1 all over negative 1 to the n plus 1 times x to the n all over n. We want that to be less than 1 for it to converge. So this thing is equal to negative 1 to the n plus 2 over negative 1 to the n plus 1 times x, or let's do n first, n over n plus 1 times x to the n plus 1 over x to the n. Okay. Oh, and this is the limit, sorry. Or not. Can you come back? No. Wait, what? See? N over n plus 1, x to the n plus 1 over x to the n, negative 1, negative 1 to the n plus 1. Okay. And again, this is equal to the limit as n goes to infinity equals the limit as n goes to infinity. That's less than 1. Okay, so let's reconcile some of these powers here. -1 to the n plus 1 over -1 to the n, or n plus 2 over -1 to the n plus 1. That's just -1 to -1. That's it. It's only 1 power extra. Okay, this thing here, n over n plus 1, I'll just leave that for now. We'll deal with that on the next step. And then x to the n plus 1 over x to the n, that's just going to be x. Now, what is the limit as n goes to infinity of n over n plus 1? This thing here goes to 1. Okay, you can use L'Hopital's rule on that if you want. It just becomes 1 over 1. Okay, and so we have absolute value of negative x is less than 1. Well, the absolute value of negative x is the same as the absolute value of x. Okay, we could break off a -1 if we really want to, but that just becomes 1. So basically it goes away. And so we get the absolute value of x is less than 1, which tells me that the radius of convergence for the power series is r equals 1. Okay. We kind of knew that intuitively because where did this come from? This came from 1 over 1 minus negative x, right? And this thing only converges if the absolute value of negative x is less than 1. It will only converge, which is the same thing that we got right here. Okay, so we kind of intuitively knew that that thing has to have a radius of convergence of less than 1. Now the interval of convergence is a little bit more complex, simply because we would have to put in the endpoints, right? It would be -1 is less than x, which is less than 1, but we'd have to test what happens with -1 and 1. And so one of these converges and one of these diverges, because if I plug in, let's just look at the series real quick. -1 to the n plus 1 times x to the n over n, right? X to the n all over n, and this is n equals 1 now to infinity. It really doesn't matter, okay? But what happens if I plug in -1 here? Okay, for x. What if I plug in the, -1? If I plug in -1 for x, that's a little sloppy. Let's write it below. Okay, let x equal -1. Then what happens is, let's see what happens here. Summation of n equals 1 to infinity of -1. I'm going to write this as -1 times -1 to the n times x to the n, which is 1 to the n, right? Or -1, sorry, -1 to the n. Okay, all over n. Okay, and so this thing becomes -1 times -1 to the nth. Let's not do sloppy math. Let's keep it nice. This is -1 times -1 times -1 to the nth power, which is going to be +1. Okay. Okay, and then I could bring one of these negatives outside. This thing here just becomes 1 to the nth power. Again, I'll try not to skip steps. So this is -1. I'm going to bring that negative outside. This is 1 to the nth power over n, as n equals 1 to infinity. Okay, and 1 to the nth is just 1, so this is 1 over n. So this is the harmonic series, and it diverges. I mean, um, and you know, the sum is going to go to negative infinity instead of infinity, but it still diverges. Okay, so -1 is out. Okay, what happens if I plug in 1? Then I get -1 to the n plus 1 times 1 to the n, which is just 1, all over n. And this becomes the alternating harmonic. Okay. And we know that the alternating harmonic is convergent. So this converges. And so 1 is in. And so my interval of convergence would be -1 is less than x, which is less than or equal to 1. Okay, that would be my interval of convergence. Okay, or we could go like this too. Either way. Okay, number 4. Okay, find a power series for f of x equals the inverse tangent of x. Interesting. Okay. So this one's a little tricky in that we're going to take a derivative or integrate in order to get inverse tangent of x. Well, which one kind of lends itself really nicely? Well, the derivative of inverse tangent of x is equal to 1 over 1 plus x squared, right? Okay, so if I were to integrate these, okay, I would get the inverse tangent of x is equal to the integral of 1 over 1 plus x squared. Okay. And if we look at 1 over 1 plus x squared, that can really be written as 1 over 1 minus negative x squared, right? I feel like we've done this already. Yes, it was example 1. Hmm. Was it though? Plus, yeah, it was. Oh, there. Oh no, we're not in. We would have to integrate that. Yeah, that makes sense. Okay, perfect. Yeah. So this is equal to 1 plus negative x squared, right? Let me write this over here. 1 over 1 plus x squared equals 1 over 1 minus negative x squared. Okay. And again, I don't want to have to do all of number 1 over again. But this is going to be equal to 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus dot dot dot, right? And we said that this was alternating 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th plus dot 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 dot, right? And so what are we going to do, though, to this thing? We are going to integrate him, okay? Integrate each term. So again, when I integrate, I got to have my constant plus x, okay, minus x cubed over 3, okay, plus x to the 5th over 5, minus x to the 7th over 7, plus x to the 9th over 9, minus x to the 11th over 11, plus dot, 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 right? Okay. Okay, so let's write a series based on what we see here. Okay, so we have our constant plus, okay, I start off with x basically to the 1st over 1, right? And then I basically, this alternates, okay? So we want to do alternating series. So -1 to the n or n plus 1. Let's think about this. Well, it depends on if I'm starting at 1 or if I'm starting at 0. Okay, and okay, can I start at 0? Yes, I can. Okay, and the reason I can is because the first thing I'm going to divide by is an odd number. Okay. If I wanted to start at 1, let's just start at 1 first, and then see if we can even start at 0. Oh, sorry, n equals 1. Okay. Okay, and then because I'm not dividing by n here, because I'm going up by odd values. So I could start at 0, but we'll start at 1 and make it easier for us to begin with. If it's n equals 1, I would want n plus 1 because I want it to be positive when I start. Okay. Okay. And then this is going to be x to the first odd value. Well, if I have the first odd value here, okay, would be 1, and then 3, and then 5. So how do I generate odd numbers? Okay, I can do it 2 ways. Okay, this is called an odd number generator. Okay, because it generates odd numbers in sequence. I'll give my eraser, please. Okay. Okay, so the odd number generator, you can have f of x equals 2x plus 1, okay, or f of x equals 2x minus 1. Okay, it really just depends on, do you want your first value to be, are you starting with 0 or are you starting with 1? Okay, because if you let x equal 0 here, you'll go 1, 3, 5. And if you let x be 1 here, you'll go 1, 3, 5. So it really depends on where you're starting. And that will generate your odd numbers. Okay, so we are gonna start with 1, so we want 2 to the n minus 1 all over 2 to the n minus 1 on the bottom. Okay, so c plus this thing. Okay, now, could I have started at 0? Sure, because I'm not going to end up dividing by 0. Okay, I would just have to switch my number generator, my odd number generator. If I start at 0, okay, I will get negative 1 to the n, and then this will be x to the 2n plus 1 all over 2n plus 1, which is maybe a nicer way of writing it. Instead of the 2x minus 1 going backwards, we kind of do 2n plus 1 start with 0. Okay, either way, that's going to generate the same. Both of those are identical summations. And so what is this equal to? This equals to the inverse tangent of x, right? So again, how could I get rid of my c? Well, I'm just going to let x be 0. Okay. So if we let x equal 0, then we want the inverse tangent of 0 to be equal to c plus, and then again, every term involves an x, and so every term is going to go to 0. Okay, since every term involves a power of x. Okay, and so the inverse tangent of 0 is 0, and so c is equal to 0, and so we can eliminate our c. Okay, and so the inverse tangent of x is equal to the summation of negative 1 to the nth, x to the 2n plus 1, all over 2n plus 1, n equals 0 to infinity. Okay, what is the radius of convergence here? Well, once again, we look at 1 over 1 minus negative x squared. That's how we, oops. That was what we used to help us generate this thing, this power series. No, that's still negative x squared in parentheses. There we go. Okay, and so when does this thing converge? Converges when the absolute value of negative x squared is less than 1. Okay, which is the same as the absolute value of negative 1 times the absolute value of x squared is less than 1. The absolute value of negative 1 is just 1. So that goes away. Okay, and then this is the absolute value of x squared is less than 1. Okay, which is the same as the absolute value of x quantity squared. And so then we can square root both sides to get rid of that squared, and we get the absolute value of x is less than 1. So the radius of convergence is 1. Okay. So this thing is centered at 0 with a radius of 1, meaning that all the values at x that work here are all values that are less than 1, or fractional and decimal values that are less than 1. Okay. Okay, that's it. Short and sweet today. Sure.